In this video, we're going to take a look at some very interesting. This one in particular, I think, is very interesting. So we're going to look at it. We are given sine of m x cosine nx dx. Now, this is going to be very tempting for you to think that, oh, gee, I could use a u substitution for the sine because the derivative is cosine. But the problem that you have here are that the arguments are different. In the case of the sine function, we have a equals mx, and in the cosine, we have b equals nx. Those are not the same. N and m are different arguments, so we can't use a simple u substitution. So we got sine a x, or sine a, and dA a equals m dx, and dB equals m, or whoops, not m, n dx. So we have cosine b and dx well, we don't want to change the argument. I just wanted to show something. Yeah, I'm running into a conundrum here. So we gotta be careful. We have to be more careful. First off, why don't we just look at this? We're gonna say, in fact, actually, let's get rid of this. Forget all we got here. Even though what I said was true, that's not a convenient way of approaching this. Now, here we use the trigonometric identities of sine, whoops, darn it, sine a plus b equals sine a cos b minus plus sine b cos a, and we've got sine a minus b equals sine a cos b minus sine b cos a. And if we add those together, we have sine a plus b plus sine a minus b equals 2 sine a cos b. And we're going to say that mx equals a and nx equals b. So here we have sine of m plus n x plus sine m minus n x. That's how we're going to go. Equals sine mx cos nx. So we replace that integrand. We have to put a 1/2. I forgot. 1/2. Because the 2, we don't want to forget that. So we have 1/2. We're going to bring that on the outside. We've got sine m plus n, whoops, can't forget the x. Yeah, we need another bracket. X dx plus sine, let's keep things consistent, m minus n x dx. And let's keep all of this business separate from our integral. And we have a great big bracket here because the half. Let's keep things consistent. Let's use the same kind of bracket. Okay. So now we can use the u substitution for u equals m plus n x, and du equals m plus n dx. We're going to say p equals m minus n x, dp equals m minus n dx. And so now we have our substitution there. We have 1/2. Let's go sine of u du over m plus n plus sine p dp over m minus n. And now we can solve these integrals. We know that if we go y equals cos x, dy equals minus sine x dx, and we have cos x equals minus the integral of sine x dx. So we have out here minus 1/2 1 on m plus n cosine of u plus 1 on m minus n sine p. And now we make our substitutions back to x. We have minus 1/2 and 1 over m plus n cosine of m plus n x. And we need a bracket around that, plus cosine, let's go back, plus 1 over m minus n cosine m minus n x, and plus c. That's our solution. Okay? We could break it up into 2 separate terms if we want, but that is the solution right here. So we can say in the end that the sine of mx dx, whoops, let's not do that, that's not right, cos nx dx equals minus 1 over 2 m plus n cosine of, let's m plus n x minus 1 over 2 m minus n cosine m minus n x plus c. And that's our solution right here. And that's all she wrote. Okay, that was an interesting one. That was one that you're definitely going to see. I can promise you that is one that you're going to see in school. So that is a problem that you're going to have to use that trigonometric identity for the angle formulas for the sine function. Now, we're going to take a look at another integral. We're going to look at dx over x times the square root of x squared minus a squared. And we use a regular trig substitution here where we say x equals a secant theta and dx equals a secant theta tan theta d theta. And now we just plug that in. So we have a secant theta tangent theta d theta in the numerator. And we have x, which is a secant theta, and we have a squared tangent squared theta plus, let's see, no, we made that wrong. We did that wrong. Our substitution was not a tangent. It was secant, so we got to get that right. I'm sorry about that. Doing it a little too hastily. A squared secant squared theta minus a squared. All right, so now we can pull out the a's. We end up, when we deal with all the a's, we got 1 over a. We got secant theta in the numerator, tangent theta in the numerator, d theta over secant theta in the denominator, and under the square root we know that tangent squared theta equals secant squared theta minus 1. Since we already pulled the a out, we've got tangent theta and these cancel. And all we have is then 1 over a d theta. And that gives us 1 over a theta plus a constant. And theta is x over a equals secant theta. So we got x squared minus a squared. And that's our solution. It was really quite simple, even though it looked like it was going to be a bear. Remember, these are problems that I've taken out from the Handbook of Chemistry and Physics. Please look it up. Look that up. I encourage you to look up the Handbook of Chemistry and Physics, especially in the front section where it discusses mathematics, where it has logarithms, trigonometry, derivatives, and tables of logarithms and tables of integrals. So it's got everything. Here's a problem that we've seen before, and we're not going to go through the full solution because we've already done this. Dx, because we have x squared plus a squared, we're going to say x equals a tangent theta. Therefore, darn it, dx equals a secant squared theta d theta. And if we now just go to a squared tangent squared theta plus a squared times a secant squared theta d theta, and we know what's under the square root is a equivalent to, we got 1 plus tangent squared theta equals secant squared theta, just as a reminder. And so we have secant to the third theta d theta, and that's one that we've already solved. And in the end, we use integration by parts. So we have 1/2 secant theta tangent theta plus 1/2 natural log of secant theta plus tangent theta plus c. And going back to our original variable, we have our trusty right triangle. We have x over a, and we have x squared plus a squared. So in the end, we have a squared over 2, and secant is x squared plus a squared over a times x over a plus a squared over 2 natural log of square root of x squared plus a squared over a plus x over a plus c. And in the end, we have to cancel out the a squared. So we have x over 2 square root of x squared plus a squared. And that's our solution for this problem. And this is one that we've solved several times already. So I just kind of blew through the solution pretty quickly. I just noticed something here. It's just being nitpicky, but it's good to be consistent. And I used that kind of a bracket. So now we've gone through this problem. I don't know why I had that one twice. I don't know. We've already solved that particular problem. And I think the same is true for the next one. So what we're going to do is just, this one's interesting actually. Even though we may have seen this before, there are aspects of this that are important. X, we got A plus B X. So let's pull out the B. So we got square root of B X and square root of A on B plus X dx. Can't forget the dx's. Now, this isn't really any different from the squares. Let's say X equals A on B u squared. So dx equals A on B times 2 u du. And then we make that swap, that substitution. So we got the square root of b out here. We've got x, which is a on b u squared. We have a on b plus x. So x is a on b u squared, and we have 2 a on b u du. So now we get rid of all the a's and b's. So we got square root of b. We have a on b u squared. We have the square root of a on b. We pulled that out, and we got 1 plus u squared. We have 2 a on b, and we make that u cubed and du. Let's do a little bit more. We've got square root of b, a squared, b squared, square root of a over the square root of b, and all these u's, u cubed, 1 plus u squared du. Oh, and there's a 2 here. So let's put the 2 out here. Now let's get rid of all of that mess. Okay, so this cancels with that. And this, we've got 2 plus 1/2. 2 plus 1/2. So that's 4 halves plus 1/2. So we have a 2a to the 5 halves on b squared. All right, I believe that's all correct. And now we have u cubed, 1 plus u squared du. And in this case, we use x. Let's use p equals let's see, tangent. No, I'm sorry. What am I doing? Let's get rid of that. We got u equals tangent theta, and du equals secant squared theta d theta. And we have 2a to the 5 halves on b squared. And now we have tangent cubed theta and 1 plus tangent squared theta times secant squared theta d theta. And we know that 1 plus tangent squared theta is equal to secant squared theta, so we end up with, boy, what a mess. A to the 5 halves b. We have, now we're going to do 1 plus secant, oh wait a minute, it's, sorry about that. We're going to erase that. All right. This is secant. Oh, wait a second. We got a cube there, so we got to be careful. Let's just write this out. Tangent cubed theta, and we got secant cubed theta d theta. Now that's something that we've never dealt with before. That's a new one. That is a new problem, and it looks like it's going to be a bear. So let us take a look at how we might want to approach it. I think, darn it, I think I might want to try a new, whoops, this is going to be a square. Can't forget the little details. All right, so we're going to use a new screen. So we have 2a to the 5 halves on b squared, integral of tangent cubed theta, secant cubed theta d theta. So now what do we do here? The best thing I think we can do is use 1 plus tangent squared theta equals secant squared theta, and tangent squared theta equals secant squared theta minus 1. So what we have here is 2a to the 5 halves. Let's just, right now, for now, let's simplify. So I don't have to keep writing that tedium. So let's say alpha equals 2a to the 5 halves over b squared. So we have alpha, and we have tangent theta times secant squared theta minus 1 times secant cubed theta d theta. And now we break it up into two integrals. We have alpha times tangent theta secant theta secant to the 4th theta d theta minus, now what do we have here? Tangent theta secant theta tangent or secant squared theta d theta bracket. Now, use a u substitution. We go u equals secant theta, and du equals secant theta tangent theta d theta. And so we end up with alpha u to the fourth du minus u squared du. And now we have a polynomial integration. So we have u to the fifth on 5 minus alpha u to the third on 3 plus constant. So now everything is copacetic. We just go back to our original variables. So here we've got alpha secant to the fifth theta on 5 minus alpha secant to the third theta on 3 plus c. Now, we have to go back to our original table where we let's go back to our original. So here, actually, we had u equals tangent theta. So we had two u substitutions. So theta equals u 1 plus u squared. So let's and u equal b on a square root x. All right, so let's copy those down. All right, on our previous sheet. Okay, so we had theta, we had u 1 plus u squared. Let's wait a minute, I'm sorry, I shouldn't have done that. Okay, cubed. I should have used a different substitution for this. I should have used p. So I'm back here, secant. So this is alpha u 1 plus u squared to the fifth minus alpha u 1 plus u squared to the third plus c. And we said that u equals a b x squared. So was that right? Is that what we had? Let's just take it real quickly. We said x equals ab u squared. So I had it wrong. Let's get that back. X equals a b u squared. All right, so we have to get this out of the way so we're not confused. And now I believe we're in our final form. We are alpha. Okay, now we have secant, where the u's there. Okay, so we have, whoops, 1 plus, now u is, we got b on ax equals u squared, and square root of b on ax equals u. So we have b on ax minus, this is to the fifth, alpha. No, we don't have alpha out there yet. We have 1 plus, that's u squared, which is b on ax to the third plus c. And that does it for us. All we have to do is now put our alpha. We have alpha equals 2 a to the 5 halves on b squared, and now we have 1 plus b on ax to the fifth minus 1 plus b on ax to the third plus c. And that's it. That is our solution. My gosh, that was a really wild integral. That was really cool. And wow. It wasn't a simple, just a straightforward trig substitution. I had to go back to the original, our original. Oh, you know what? Darn, I forgot. Oh, please. This is over 5, over 5, over 3, over 5, over 3, over 5, I almost forgot, over 3. So that's it. Okay, see, you just have to be careful. You have to be careful. That is, but this does it. This is the correct solution for the integral, for the original integral, which was x square root of a plus bx dx. So that's the solution. And this is where, again, you have to be careful. I almost forgot those critical constants. But we didn't in the end. We did remember them. So that's it. And this completes my first page of methods of integration. In my notes, I have a whole second page that we can cover of some very fascinating integrals. So with that, I bid you adieu.